this lecture is on elastic collisions. In an elastic collision, two objects collide and bounce off of one another. Let me show you that, and then we can see here that A and B collide into one another and they bounce off from one another. And what this means is that both momentum and kinetic energy are conserved. This is the only type of collision in which energy is conserved. So if you have inelastic collisions, energy is not going to be conserved. This will give us two simultaneous equations to solve to predict their motion after the collision. So remember when we had to do those force problems in which we had to do two different directions to solve the problem? Same thing here. So here the momentum of particle A plus the momentum of particle B has to equal the momentum of particle A after the collision plus the momentum of particle B after the collision. Okay, so in this one you can do energy conservation. So the energy you start with has to equal the energy you end with, but also the momentum you start with has to equal the momentum you end with. Okay, so here, when we add these together, let me get these vector signs on here because this is not quite correct. Otherwise everything looks bolded to me. Okay, so this basically says that the momenta I start with has to equal the momenta I end with. And we know that momentum is mv, so we can replace the PA with MAVA, and so on. And it also means that the kinetic energy we start with here has to equal the kinetic energy that we end with. So you can see that there's a relationship between mass and your speed for your energy equations and the momentum equations. But keep in mind that up here, this is a vector, and this is not. This is a scalar. So this is a vector, this is a scalar. But that doesn't mean that you can just take the total velocity. Remember that for your energy equations, you do have to make sure that you're going in the same direction. So you might have to use the x component of the velocity to calculate the kinetic energy in the x direction. So just keep that in mind. Since both of these equations describe the motion of the same system, they must both be true. Hence, they can be solved as simultaneous equations. That will be done on the next slide, and an interesting result will appear. So let's get our vector signs back up. Okay, this is one of the things conceptually that you need to remember, is that for energy, it's not a vector quantity. For momentum, it is. You forget the vector sign, and that's okay when you're solving problems, unless you forget to put in the direction into the equation. That's where you can go wrong with these. Okay, so here we go. Conservation of momentum tells us that m1v1 plus m2v2 has to equal m1v1 prime plus m2v2 prime. Okay, and then you can see that if I put all the m1s and all the m2s on one side, and the other on the other side, you can see that we get this relationship. Okay, over here we have 1/2 mv squared for particle 1 plus 1/2 mv squared for particle 2, and that equals to the same thing only after the collision. Notice that I can divide both sides by 2, or I'm sorry, multiply both sides by 2, or divide both sides by 1/2, and the 1/2s go away. And so notice here it's a little bit different. So now you end up with m1 times v1 plus v1 prime times v1 minus v1 prime. But notice no vector signs. Okay, no vector signs. Okay, so if I divide both sides by actually, hold on. Let's see what they're doing here. Oh, I see. Okay, so here we have equation from energy, and here we have the equation for momentum, and we assume that we have already divided through by the unit vectors. So this is the scalar equation that's left. Okay, so you've divided both sides by I hat. See the I hats here? And remember that we can just cancel them out. Okay, so this shows how we can get this equation here. So you end up with V1 minus V2 is equal to negative V1 prime minus V2 prime. Okay, and that's because we can cross this one out with this one, and this gets crossed out with this, and we can cross out this term and this term and this term and this term. Okay, and that's because we took this equation here, and we took this equation here, and divided the energy equation by the momentum equation. By solving the conservation of momentum and constant kinetic energy equations simultaneously, this is the result we get. Okay. Do you recognize the terms on the left and right of the above equation? What does it mean? Two objects have an elastic collision. Before they collide, they are approaching with a velocity of 4 meters per second relative to each other. With what velocity do they move apart from one another after the collision? Okay, so for this one, they're both approaching each other. So one of the objects is going to be traveling east and the other is going to be traveling west. I want you to go ahead and see if you can figure out with what velocity they have after the collision. Pause the video now. Okay, hopefully you didn't spend a whole lot of time doing all those calculations of finding the conservation of momentum and the conservation of energy. It should be 4 meters per second away from each other, and here's why. We have V1 minus V2 equals negative V1 prime minus V2 prime. The difference in the initial velocities is the same as the negative difference of the final velocities. So what does that mean? Well, here we have, we would have one going 4 meters per second and the other going negative 4 meters per second. So the relative velocity between the objects before the collision is equal to the negative of the relative velocity between the objects after the collision. Okay, so if this is going to be 4 meters per second minus 4 meters per second, or minus a negative 4 meters per second, sorry, that's going to give you 8 meters per second. And that means over here also has to equal 8 meters per second. Because the masses are equal, we have two objects, well, actually it doesn't tell us that they have equal mass. But since they're approaching both with the same initial velocity, we're going to assume that they also have the same mass. That's really not something you want to do. You really want to make sure that they do have the same mass before you make that kind of an assumption. But also remember that this equation already took into consideration that you had two different masses. And those masses canceled out when we divided the energy equation by the momentum equation. Okay, so I was wrong in saying these two have the same mass. We can't really make that assumption. But we certainly can use this equation to figure out that they both have to have the same velocity leaving as they had coming in. Two objects have an elastic collision. Object 1, M1, has an initial velocity of 4 meters per second east, and M2 has a velocity of negative 3.0 meters per second, I hat, or west. After the collision, M1 has a velocity of 1.0 meters per second. We're going to assume that there's a plus sign right there. So let's put a little plus there and give it an I hat. Let's go ahead and make these I hats as well. What is the velocity of M2? Go ahead and pause the video now and see if you can solve this problem. Okay, let's see if you have the right answer. Okay, I'm going to go ahead and get my pen out. We know that the initial velocity was 4 meters per second I hat. The initial velocity for particle 2 is negative 3 meters per second I hat. V1 prime is 1 meter per second I hat, and we want to solve for V2 prime. We're going to go ahead and use our equation. The V1 minus V2 is equal to negative V1 prime minus V2 prime. Solving for V2 prime, we end up with V1 plus V1 prime minus V2. Substituting in our numbers with our unit vectors, we end up with 8 meters per second. Now you might be saying, wait a minute. Why is this 8 and not 5 minus 3, which would be 2 meters per second? Remember that this is minus, but the direction is negative I hat, and that makes it a plus right here. So you end up with a minus minus, which is plus. So your answer should be 8 meters per second I hat. Okay, two objects have an elastic collision. Object M1 has an initial velocity of 6 meters per second, I hat. And M2 has a velocity of 2 meters per second, I hat. After the collision, M1 has a velocity of 1 meter per second, I hat. What is the velocity of M2? Okay, go ahead and pause the video and see if you can solve this one. Okay, so let's take a look and see if you got the right answer. Writing out our given information, we have V1 is equal to 6 meters per second, V2 is equal to 2 meters per second, V1 prime is 1 meter per second, and V2 prime is what we're looking for. Using our equation and solving for V2 prime, substituting in our numbers with our units and unit vectors, we end up with V2 prime is equal to 5 meters per second. One thing that I would like to, for you to be careful about is when you're solving these problems, please don't just write down the numbers without any units or without any formulas. Remember that on the AP exam, they're going to give you points for writing this. So you probably get a point just for writing this equation. You probably get another point for putting the numbers in correctly with the units. You probably get another point for having the correct number of significant digits in the units in the final answer. They're not going to give you any points for the 5. What they will give you points for, though, is sig figs and units and direction. Okay, that concludes this video, and we'll go ahead and get started on the next video when you click on the next one.